Okay, so this video is just meant to go over with you how the kinematic equations kind of came to be. So if we think about the kinematic equations, there's three. There's V final is equal to V initial plus AT, and that actually just comes out of our definition of acceleration, right? Acceleration is just a change in velocity over change in time. Then there's our second equation, delta x equals V initial t plus 1/2 AT squared. And then there's the third equation then, BF final squared equals V initial squared plus 2A delta x. So we're going to just go through and derive how it is we found the second equation and how it is we found the third equation. So the second equation actually comes from looking at our velocity time graphs. And so what we kind of looked at before was that the area under the velocity time graph is just equal to the displacement. So in this case, if I have a velocity of 10 meters per second, constant for 3 seconds, my displacement is just like this area here. And it's pretty easy to find. In this case, like the area is just equal to the height of my rectangle times my base, which if area is equal to the displacement, that's just my delta x is equal to my height. So just my constant velocity times my base, which is my change in time. And that's just our familiar equation that distance is equal to rate times time. So in this case, it would just be my 10 meters per second times my 3 seconds. So my delta x is just equal to 30 meters. So it's pretty easy and simple if I have a constant velocity. But what happens if I have a changing velocity? Specifically, if I have a changing velocity under a constant acceleration situation. So here I've got a graph where my velocity is changing. It's a constant acceleration because I've got a linear line here. So again, we're going to look at the fact that my displacement is still going to be the area under my curve. But now I kind of have like this, right? Looking at the movement of that. And so that is specifically saying, okay, well, what is this region? Plus, I've got this region. So it's almost like I've got like a region, I'm going to call this region 1, and this region 2, because it's the area under the entire thing. Well, region 1, so for region 1, the area is a rectangle, and for region 2, it is a triangle, right? And so my total area would just be the sum of the area of my rectangle and the area of my triangle. So if I think about area 1, area 1 is just like before, where it's going to be equal to my height times my base. So that's just going to equal my velocity times, and it's my initial velocity, right? It's like whatever this initial value is, it's this height. So it's my initial velocity times my time, okay? So that's my area 1, call it area 1. And then for my area 2, it's a triangle. So area of a triangle is just 1/2 height times the base. So in this case, my area 2 is going to go 1/2 my height. Now my height is just the height of this triangle. So it's like going from here to here, which is like a difference in velocity. Okay, it's a change in velocity. So it's like looking at my change in velocity times my base, which is my time there. And we're actually going to utilize one other kind of substitution equation, and it's this equation for acceleration. So we know acceleration is equal to a change in velocity over change in time. So I could actually rewrite this and say that change in velocity is just equal to acceleration times my change in time. And I've been writing t everywhere, but really it is change in time. So if we take this concept and plop it in there, we end up getting that my area 2 is equal to 1/2, and then instead of having delta V, I'm going to put this area times time. I'm just going to leave it as t, because my time initial is just 0, and then times t again, and that gives us that area 2 is equal to 1/2 AT squared. So then if I think about my entire, kind of running out of room here, my entire displacement is just, my delta x is my area 1 plus my area 2. So my delta x is going to equal my area 1, which is just v initial times t, and then my area 2, which is 1/2 AT squared. So that's where we get the second equation. Now where we get the third equation actually comes out of just the definition of average velocity and looking at the definition of acceleration. So again, we know the equation for acceleration is change in velocity with change in time, and actually we can write this as, that acceleration is equal to v final minus v initial over time, right? It's the same kind of a thing. And then we can get that iteration of this as well. Now the equation for average velocity, so average velocity can also just be thought of as the total displacement over the total time traveled, okay? And that's just looking at our equations for velocity. So an average velocity looks at the total displacement I've traveled divided by the total amount of time that it took me to travel. And then we kind of think about how else could we calculate average velocity? Average velocity could also be thought of as just my final velocity plus my initial velocity divided by 2. And that just comes out of the definition of average, right? So if I were to set these things equal to each other and say, well, if this is average velocity and this is average velocity, could I set those two equations to each other? And you definitely can. So I'm going to bring those here and say, well, my VF plus the initial over 2 is equal to my delta x over my delta t. And again, I'm just going to call it t because time initial is usually 0. And this now comes to be like the mystery of how would you know to derive this? You wouldn't necessarily if you were just a layperson, but I'm just going to walk through the steps. So I'm just going to cross multiply and get things just kind of on one level here. So I'm going to bring my t over here and say t is equal to v final plus v initial, and then 2 times delta x. So again, all I've done is I've cross multiplied those things. Now, I also want to bring in my value for acceleration and get rid of my value for time. And so that's going to come in with this equation. I could rewrite this equation up here. If A is equal to VF minus VI over T, then I could just say, well, T is equal to VF minus VI over A. So I've just kind of swapped those two things. Okay? So that's another expression for time. And I'm going to take this expression for time, and I'm going to bring it in right there. So that gets me this VF minus VI times VF plus VI divided by A, right? And it's divided by the whole thing by A is equal to 2 delta x. And again, I'm going to bring this over here to kind of get it all onto one playing field. So VF minus VI is VF plus VI is equal to 2A delta x, and it's kind of starting to look familiar like that third equation. And then if you look at this side over here, you have VF minus VI times VF plus VI. And this actually, if you FOILed it out, first, outside, inside, last, this shakes out to be just a difference of squares. So this actually is VF squared minus VI squared is equal to 2A delta x. I know that property from math, it's finally used. And then we just rearrange it to be VF squared, I'm going to add that over, is equal to VI squared plus 2A delta x. So that is where that third equation comes from.